Now let us have this example, which could be applicable to astronomy when you get a light from a very remote star, or it could be from a satellite getting the power spectral density from one particular point or other application. In this example, we assume that you are transmitting, or a source of signal is transmitted with this equation, and you receive this source at another location, assuming that either transmitter or receiver, they are moving. So if you have some relative velocity, so r is stretching factor, which could be a little bit bigger than 1 or smaller than 1, and it could be relative close to 1 usually, if the velocity of the object is relatively smaller than the wave propagation. So these could be applied to sound signals, or it could be applied to electromagnetic signals. So if you put this S and then put it in this equation, you can establish this one. Obviously, you could absorb this A into this S, and you could absorb these 2 into this S and BI. So in that case, you have to define BI is equal to this one, and so on. So the way you can get this expression is that e to the power j omega naught TR and e to the power of minus, and this is 2R and e to the power of j omega naught TR. So you write this one as this one, and then multiplied by ASI, and then you have a sum. So this is your BI, and this you write the order here, R and then T, and then this will become WI. So here at the receiver, you have the set of frequency WI instead of omega I. So frequencies are shifted, the frequencies are different. And the amplitudes are also different with the amplitude of the transmitted signal. They are multiplied by AI, because different frequencies, they may be amplified or attenuated differently at different frequencies. And they're also phase shifted. So but even though that these are different, we may still be able to recognize that which one correspond to which one, and then solve lots of practical problems. So if we assume that these SIs are independent or BIs are independent, so if we assume that BIs are independent and sequence of random variables with mean of 0 and different variances, obviously you could assume that these variances are, let's say, related to variances of these SIs and so on, but let us not complicate the problem. You may make different assumptions about other parameters like 2 and so on. You may not know them. You may assume that they are deterministic or random if you know their distribution, and they use it in different applications. Different assumptions are made. Here we make a very simple case, and we assume that these are like deterministic, constant, and so on. So using them, for using this equation, I could try to calculate the autocorrelation of received random process. Obviously, this is x of t1, and this is x of t2 conjugate. Now, here I used a different dummy variable because I want to merge these two summation and write it in double sum. This double sum, and nothing is random in these boundaries of this summation, so I could change the order of this expectation and this double sum, put it outside, so I get this expression. So these two guys are constant. They are multiplied together, and then they come out of the expectation. So this gives you this one, and then this one, mean of BI, BK conjugate. If I assume that this is equal to 0 for I not equal to K, and is equal to sigma 2 BI, when I is equal to K, then this double sum becomes a single sum. Obviously, in this case, if the the energy, if the component of different frequencies, they are uncorrelated, this guy will be only a function of time difference. This is T1 minus T2. You don't see anything else. So this will become wide sense stationary. Remember that this guy is already wide sense stationary if these SIs are independent or uncorrelated. So if you take the power spectral density of this one, you get this expression. And if you take this one, the power spectral density of this one will become this one. So this frequency omega I is converted to frequency Wi, and then the variance of Si is converted to variance of Wi. So they may be proportional and so on. Okay, and then you may be able to solve lots of practical problems using these relationships.